on this computer. I didn't do it on Monday either. And so I had to, in the hour between this class and my next class, I re-recorded the lecture. So Monday's lecture is up, but thank you for letting me know so I don't have to do that again. In any event, I should say again then for people who weren't around here, just in case all they're going to do is review the video, which is their choice. The focus of the exam, I guess, in the sense that perhaps a third to a half the questions are going to be on it, is the material we didn't have on the last midterm. That's worksheet 28 through today's worksheet 37. That's magnetic forces through Faraday's law, through through electromagnetic waves, interference, diffraction, and then of course today what we're going to be talking about reflection and refraction. Okay, I'd expect a little bit longer than the second midterm. That was, I think, 20 questions on the second midterm. I'd be looking more around 30-ish questions, and that's what you can expect. It should be posted next Tuesday, and it'll be due Thursday sometime, and that's it. All right, topics for today. Last two things we're going to be doing this semester are refraction and reflection. We'll start off with reflection. Let me share with you my my PowerPoint here. Make sure I'm on the right page. Share that, and let's go back to where we're starting. There's the stuff we did last time, and I do want to just go through a little bit of history of the measurement of the speed of electromagnetic radiation, and who did it, and who were fairly accurate on it. And, you know, Galileo tried to do it too. He had this idea of unshuttering some light, seeing how long it takes to travel down a long hallway. And, you know, the best he was able to do it with a measurement in his day is it's very fast. There was a thought it was even infinite. Okay, an astronomer in the 1700s by the name of Raymer, he looked at the period of Jupiter's moons, and as they were predicted to appear, and as they did appear, with some estimate of how far away Jupiter is, tried to calculate what the speed of light might be for the light to get from one of those moons to his telescope, and all he could figure out was it's very fast. But he ruled out an infinite speed. He did note there was some time delay based on predictions to when things were observed. And so his best estimate is fast but finite. And then finally, and I think I mentioned when we were talking about Maxwell's equations, while Maxwell is predicting the speed of light, the speed of any electromagnetic radiation theoretically, concurrent with that is Michelson, who's a professor at the Naval Academy at the time in Annapolis. He does some initial measurements right there in Annapolis on the campus of the Naval Academy, just to prove his experiment would sort of work. And then he took it to the West Coast and made fairly accurate experimental measurements of the speed of light. If you've ever been in I think this is in the San Diego, Los Angeles area, Southern California, he set up his experiment between two mountains, okay, Mount Wilson and Mount San Antonio. And a clever device on how to do this. It's actually a faceted mirror, and this particular one has 8 sides. If you ever get to go to the Naval Academy, you get into the science building, there's a display of one. It's hand cranked, and it's got 4 sides. And the idea is, based on this distance right here and the light going across, you're hoping that the facet that it bounced off here would just rotate over to here. And if you turn the hand crank at just the right speed, an observer will be able to see the light source as it rotates. You know, there's some timing issues of making sure you're getting the right facet, but from this this kind of clever experiment, way before lasers, Michelson was able to make a reasonably accurate measurement of the speed of light. Okay, and we have from Maxwell his experiment, his theoretical prediction that hopefully corresponds to the experiment. We had said that the speed of light, which is such a fundamental quantity in physics, we give it a constant c, pretty prestigious position to have the constant c for a parameter, speed of light in a vacuum. And we had said that it was the square root of 1 over the permeability of free space times the permittivity of free space. And no kidding, you put those numbers in, you get 3 times 10 to the 8th meters per second. And so what if the light, the electromagnetic radiation, isn't going through free space? Air is close to free space, but certainly a vacuum is free space. What if it's going through, say, a piece of glass or a piece of plexiglass or water or some other transparent material? Or if it's just electromagnetic radiation, is it going through something that's just transparent to, say, ultraviolet rays or transparent to radio waves? What would we expect the speed to be in that case? And hopefully you realize all I have to do is figure out what the permeability of a material is and the permittivity of a material is. And it would be logical, I think, that I would just take those two, multiply them together, take the reciprocal, and then take the square root, and that should be the speed of light or the speed of the electromagnetic radiation moving in that material. If it's transparent material, light will work just fine. But think about going to rubber, and maybe you can have you have rubber coatings on antennas. The electromagnetic radiation that the antenna is picking up is still going through that rubber, and so it has a speed while it's going through that rubber, and it's transparent to the rubber is transparent to AM radio or FM radio, for example. Well, hopefully you recognize that we had a parameter that allowed us to figure out what the permittivity of a material was, and that was called the dielectric constant, right? And we did that when we were talking about capacitors. We often had just air in between the plates of the capacitor, but then we talked about, well, what if we put some kind of material in there? What happens? Well, it changes the permittivity of the material from that of free space to something else, and there was just a constant called the dielectric constant. I've listed a bunch on this table, okay, that changed the permittivity of free space into the permittivity of material, and then was useful for calculating the capacitance of a capacitor with a dielectric material inside. Okay, great. We never really talked much about that for magnetism. Perhaps you remember when we were looking at Faraday's law in my basement lab, I took a piece of iron and I put it in between the two coils that were concentric to each other, and the response was significantly bigger. And what I did is I used one of the three naturally occurring materials that are magnetic, ferromagnetic. I used iron, okay, because iron, cobalt, nickel are those three materials. And for those three materials, the permeability of the material and the permittivity of free space are drastically different. For every other material in the universe, they're pretty darn close. The difference between the permeability of the material and that of free space is inconsequential. Sometimes the material causes the permeability to be just slightly above that of free space, sometimes just slightly below. But the constant here, which would be analogous to dielectric constant for all but those three materials, iron, cobalt, and nickel, is just about 1, maybe a little less than 1, a little bit greater than 1. Ignorably different is, I guess, the point. And so if I'm going to find the speed of light in a material, I'm going to take the permittivity of the material with the dielectric constant, which is nowhere near 1 for very many materials, and the permeability of the material, which is very near the permeability of free space. And you can see I can just factor out that square root of the dielectric constant in the denominator there. And then I just have the speed of light in a vacuum divided by the square root of the dielectric constant. And so one of the factors that we come from this by just looking at values that chemists in many cases have determined for dielectric constants of material, they're all greater than 1. Look at the difference between a vacuum and air, and that's why I use the two interchangeably. That 6 there is pretty inconsequential. But for other materials, it is a substantial difference. That always means that in a material, that speed has to be less than the speed of light. Speed of light's kind of an absolute constant. And if you ever read somebody who says something about they found a way that electromagnetic radiation is moving faster than the speed of light, read the details, because there's always a little asterisk on that. We believe that's an absolute maximum, and that in any other material, the speed is less than the speed of light in a vacuum. Okay, and so that's our conclusion. Oddly, not by making speed of light measurements, but by making measurements of dielectric constants of materials, which could allow electromagnetic radiation to travel inside of them. All right, that's that square root of the dielectric constant, okay, that I just talked about, has come to be given a name and a symbol. The symbol is N. It's called the index of refraction. And if you look, you're going to find it's not exactly the square root of the dielectric constants I showed you on the previous slide. Water is a huge exception. And if you know something about water, van der Waals forces and things like that. You look at water's dielectric constant, it's 80. Square root of 80 would be just a little under 9, I guess. And yet when you come over here, you find for water, the dielectric constant is nowhere near 9, which is what you might predict from this order of magnitude first order approximation. There's a lot of other factors that go into water, but for many materials, it's darn close to the square root of the dielectric constant. And one of the things you always have to remember about dielectric constants and then index of refraction is what frequency, what wavelength were you making this measurement for? Okay, and you can see on this chart, these are all made for a particular wavelength, which is pretty close to the center frequency of the light coming from the sun. You do some other use some other frequency, you're going to find a significantly different number. We call that dispersion, right? When we see that different colors of white light get refracted by different amounts and we create rainbows and things like that. We'll finish up talking about that. It's because different, this number right here that we talk about as a constant is slightly different for different frequencies or different wavelengths of light. And that's true for any of the numbers on this table. So always pay attention to that. It's an important aspect. And that's often why there's a difference between the square root of the dielectric constant and the index of refraction. And it's just one of those things you got to keep in mind. These are nominal numbers. Any physics problem, whatever number is on the table, that'll be the number you can assume is the right one for the frequency of light that I'm giving you. Okay, so that's a dielectric constant, and that's a index of refraction. You can see how they're related. This table is something that will always be available to you to look up, and you can find these numbers on the web. And the difference between this number and what you might find on some other table is inconsequential to any problem. All right, here's another set of tables I got, exactly saying the same thing and reminding us that varies with the frequency of light. All right, so here's our model then based on that. And so let's say that we start with light in air. And, this time, so I'm using rays. I'm not doing these wave fronts that I was drawing the other day when I was talking about interference and diffraction. Just not. I only care about the ray here. And if you remember, we were saying, is light a particle? Is light a wave? Which is it? Well, it depends what property we're observing. It's as a reflected ray happens. Okay, I don't need it to be a wave in order for that to happen. The pool table in my basement, I put the ball in at some angle, it reflects off the wall, off the rail at exactly the same angle, just like a particle would. You throw a ball off the wall, you'll see, exactly this law. And light, it exhibits a particle property, and that the incident, and notice the notation here, that's the incident angle and the reflected angle are the same. Okay, and that's nothing new to mechanics. You might have expected that from collisions when you were conserving momentum last semester with Dr. Tech. Okay, and of course the index of refraction in this material here, maybe it's air. Is often where we start because we can easily put a source in air. That's the notation that we're going to use. And sometimes I'll go N1 as well. Okay, so it's either the incident or 1. They correspond to each other. And then there's, and oh yeah, in the same breath, this will often be 1. And I'll leave that reflected right there. So the incident angle is 1 in this material, material 1. I incident 1. All right, there's also a transmitted ray though, that is refracted, as we said, okay, in the transmitted medium. Often we'll say that's N2, the second material. So it's going from 1 to 2. I like going top to bottom or left to right, but there's no requirement for that, obviously. And what you'll notice here is the angle over here has been observed over time to be different from the angle here when you change the index of refraction. Okay, so the transmitted ray has a different angle as it moves through, and that's our model. Okay, for what happens to light when it hits an interface between two different materials. This might be glass, for example. Like in a window, we go from air to glass and the light transmits from one to the other, a very common application of this. Now, I have an animation I want to show you of how this works, particularly on this transmitted ray. We'll talk a little bit about the reflected ray after I show you this animation. So let me jump out of here real quick and show. And then now I can discard those guys. And I thought this was a pretty good animation of what's going on. I think I mentioned earlier in the semester I rely on the animations of a guy up at Penn State who's also an acoustician colleague named Dan Russell. And so I want to share Dan's, if I can find it here. Is that Dan? Yep. Okay, there it is. I want to share Dan's simulation here. And what you're seeing is maybe this is light. Hopefully you're seeing a light ray in medium 1. Okay, and it could be sound too. Dan's actually an acoustician, so he's talking about sound here, but it could be any wave. Starts in medium 1 with some wavelength, and you can see the difference between the wavefronts here are one wavelength, and there's the ray that I've been talking about. There's the incident angle, and when it hits a second medium, and in this case the medium has a speed of light or an index of refraction that's greater than 1 or greater than what you had in medium 1, and you can see the light or the sound bending with a different angle, and it's bending towards the normal to the surface that is the refraction surface. So as we've defined theta 1 and theta 2 here, the angle gets smaller when I go from a slower sound speed to a faster sound speed. But you should observe one other thing that has to be happening. What you should be observing, and I know it gets a little hypnotic after a while, I'll stop it in just a bit here. You'll see that the wavelength is getting smaller when you go into the slower speed material, the slower speed of light or slower speed of sound material. And it has to be, okay? Because if you remember, the speed of light is equal to the frequency times the wavelength. What we've found is that frequency stays the same. The wavelength must change as the sound speed changes when you take light from one material to a second. A couple of reasons why the frequency has to be the same. I'll give you 2 arguments. Frequency is directly related to the energy and the power in the wave. And we think just going through a boundary by itself doesn't cause you to lose energy. Energy gets dissipated over longer distances. Merely going from one medium to another isn't enough of a distance to actually cause any loss of energy. And so for that reason, it doesn't make sense, since energy is proportional to frequency. It doesn't make sense for the frequency to change. But on a more physical sense, if you think about frequency being the number of wavelengths that hit per second, it's the number of cycles that hit per second. If it wasn't the same in medium 1 as in medium 2, you would get wave fronts piling up right at. They'd be coming in at a rate greater than they're going out, or coming out greater than they're coming in which case you'd try to be pulling the wave apart, pulling it into a vacuum. And that isn't something that's observed. And so the frequency stays the same. And as you can see here, when you go from one medium to another, the wavelength does change, in addition to the fact that it gets kinked. Okay, and of course, reflection would just be a wave not shown going off with the same angle as it came in. A little easier to visualize, I think, so it's not on this simulation. All right, so hopefully that gives you a good picture to look at. Let's go back to what I was talking about, and we'll focus in now for a bit on the reflecting aspect, and then we'll talk about the refracting aspect, and then we'll talk a little bit about dispersion, and I guess we'll call it a course then. So let's move on right here. I talk about these 2 laws. I just said reflection, incident, reflected are the same. And the law that governs the angles when the light is refracted is referred to as Snell's law. And it says the index of refraction going in is equal to the sine of the angle going in, and realize that angle is with respect to the normal to the surface. So a refracting ray would be right there. The angle is on theta t here with respect to the normal to the surface. And I should warn you, there are folks doing research who choose to use the other angle right here, the angle with respect to the surface. That's a little bit unconventional, more so in sound waves. You see people talking about the other angle here, the complementary angle. This equation with its angles and the trig function of a sine is associated with these 2 angles, and this third angle here for the transmitted angle with respect to the normal. Okay, and if it was the other angle, you'd expect a cosine and you'd be right. Okay, so if you ever see Snell's law written with cosines, take a good look at how the angle is defined. There's actually something a little more general about physics equations that I would always warn you about. Anytime you got a physics equation, there's always a picture of something that goes along with that equation. right? Sometimes people try to reduce physics down to just a series of equations that you plug in and plug numbers into to get answers. And while there is some truth to that, you really have to know the picture that's associated with the equation. And if you've got both of those, well, then I would argue you're right. Then physics, often at the introductory and intermediate levels, just comes down to, okay, figuring out what the right numbers are. But there's often a picture that's associated with it. I can't tell you how many times I watch people use equations to solve for, say, electric or magnetic fields that have absolutely nothing to do with the electric or magnetic field of a problem, but they found an equation that allows them to calculate something, and it's the wrong something because it's not the right application. And in this particular case for Snell's law, you really, when you're learning the law, even if you look it up, you got to have this picture of where the angles are defined, because it doesn't have to be that way. It could have been another angle that was defined. And so pay attention to that. And then it's a fairly trivial problem, really. You'll have four unknowns here, right? Index of refraction, angle coming in, index of refraction, angle coming out. You'll be given 3 out of the 4 of those things, but you got to just make sure you have the right angles and the right index of refractions in accordance with that picture right there. Pretty straightforward stuff, I guess. All right, let's talk a little bit more about reflection. Okay, I have 2 types of reflections I like to talk about: internal and external. And if you're going from like an air to a water or an air to a glass, most people would say you're on the outside with your source. That's an external reflection. Every now and again, though, you put the light source underneath the water, for example, and it bounces off the surface of the water, going from water to air. Okay, I would call that an internal, because all of a sudden I put the light source inside the medium that isn't air. Okay, and we'll see examples of that here in a bit. So those are 2 terms of art associated with reflection. We also talk about specular versus diffuse reflections. And in truth, everything is diffuse to some degree. But if the light rays come in and they all hit a surface so that they come off parallel, we refer to that as a specular reflection, like a mirror. Okay, other objects you can see, there's angle of incidence, angle of reflection, but if the object surface is kind of rough, well, that could cause some scattering of the reflected light. It may predominantly go in a general direction that is the same, but it isn't as perfect as the ideal specular case. And so what we're going to be talking about here for the next couple of minutes is the specular reflection, because we're going to show how to create images. And too bad we don't have more time to do curved surfaces, but let's talk about plane mirrors and see how we form an image. And let's say we've got a plane mirror right here, maybe like the one in your dorm room or in your bathroom at home, okay? And that, I don't know, maybe that's your foot or something like that, because I put it down below. And we call this distance right here the object distance. It's how far in front of the mirror you are. And the light comes in, incident angle, drew a normal to the mirror, reflects off at the same angle, appears, if you had your eye right here, it appears to be coming from some point back behind the mirror, right? That's where that light appears to be coming from. It actually came from your foot, bounced off the mirror and came that way, but it appears to be coming from this dash line someplace back behind the mirror. Let's draw a couple more angles here, I guess. There's a neat angle. It's the 0 angle, right? Okay, so the light comes in and comes straight back. Interesting. Let's pick an intermediate angle like that one. Light comes in, reflects off, and you can see there's this point back here where if somebody is looking from off over here, the light appears to be coming from. And I see my dots a little off. We call the location where the light appears to be coming from behind the mirror, we call that the image back there, and we call this thing the image distance. Now, our textbook just uses the prime for the image distance. I throw in the I just to remind you that's the image. Now, this particular image has a special name because the light isn't actually going through the mirror. This is not a transparent piece of material. There's often a piece of metal with some glass on the front of it. So the light isn't actually coming from back here. We refer to this as a virtual image. And I'll show you an example of a real image here in a second. We'll do it with refraction instead of reflection, but this is called a virtual image because the light only appears to be coming from here, and that is the definition of a virtual image. A real image might be if I was projecting my PowerPoint notes on the slide at the front of the room in La Trenta. Okay, that's a real image. It's actually putting light rays on a screen. You can see if I tried to put this on a screen, if I put a screen back here behind the mirror, it would see nothing. There'd be no light actually reaching the screen. That's kind of a working person's definition of what a virtual image is. Okay, and in a plane mirror like this, you can see that these two distances, the image and the object distance S, image distance S prime, they're the same, okay, for a plane mirror. If I curve the mirror, which I don't have time to do this semester, they wouldn't be the same. All right, virtual image. So here kind of begs a question. I always laugh at this. People buy these big, long mirrors that have been designed because you figure in order to see you, this could be your height right here, you know, your 5 whatever feet is Y0. There's your foot standing on the floor. There's the top of your head right there at the head of the arrow. That's the way optics people often draw objects, just as upright arrows, right? So stick figure people, I guess. How big does your mirror actually have to be so that you can see your entire body from your feet to your head? And a couple tracing of rays like we've been doing here, where you cause the angle of incidence to be equal to the angle of reflection, okay, shows you that you don't need a mirror that comes all the way down here just to see your feet, because your eyes are up here near the top of your head, and all you got to do is make the angle of incidence be equal to the angle of reflection, and you should be good to go. So in fact, the mirror really only needs to be about half of your height in order to see your entire reflection in the mirror. And you know, I do laugh at these big tall mirrors. They look kind of cool, but are they absolutely necessary? No, I guess this part right here just allows you to see the floor in front of your feet pretty well, right? I mean, that's what you're getting from that. Okay, and so that's just a thought. You know, when you're remodeling your bathroom in a couple of years in the house or the apartment that you live in, think about how big your mirrors, no kidding, actually have to be. All right, that's enough. A couple other aspects of reflection that I want to point out. If you put two mirrors at 90 degrees with respect to each other, you look, angle of incidence, angle of reflection right there, and then draw the normal right here, okay? This must be 90 minus the angle of incidence. That must also be 90 minus the angle of incidence. And that means that the ray that came in and the ray that came out, although shifted a little bit, okay, by the size of these two mirrors here, come out parallel. They come out parallel. The ray comes in and the exiting ray comes out parallel as long as this is a 90-degree angle. I guess the reason this is important, let's go to the positive side. Let's say you're making a road sign and you want the letters on the road sign to be very reflective. You would want this to happen. So the headlight beam comes in, you want the light that's reflected from the road sign to come right back to the headlights. And so you want this 90-degree. A number of the adhesive companies sell tape. 3M, I think, makes this. If you look really closely at the tape, there's little cubes that are put in there, embedded in the layer of the tape, plastic little cubes that cause this to happen, and the tape is very reflective. House numbers, often on a mailbox, for example, are made out of the same sort of tape with corner reflectors, literally putting a bunch of little crystals about the size of salt crystals in the layer of tape, oriented randomly so that the light always does this and reflects back towards the source. And if you want something to be reflective, 90-degree angles with mirrors are the best way to do it, and little cubes in a piece of tape meet that function. On the other hand, if, say, you're building a warship or you're building an airplane and you don't want it to be reflected, well, just take away all the 90-degree angles in the design of the warship or the airplane. And if you look, the Air Force and the Navy's stealth fighters, okay, are all built with profiles that minimize 90-degree angles. So if a radar, for example, or an infrared sensor or a laser sensor illuminates the aircraft, if there's no 90-degree angle, the light will be scattered off at some angle other than where it originated, and it doesn't give an image back to the source of the radar, and makes the warship or the airplane less detectable. And so a lot of technology with this very simple idea eliminate the 90-degree angles in the design of the architecture of the craft that you don't want to be seen. Pretty impressive. We say stealth technology, and all it means is get rid of the 90-degree angles wherever you can. Now, I will tell you this, there's also some coatings that you put on these stealth aircraft and ships that are anti-reflecting, much like the coating, anti-reflected coating on the lens surface. You can do that same sort of technology. I'd love to be able to explain more of that to you. And we had another week, that may have been something we talked about with interference, because it actually is an interference phenomena. But as a first principle, stealth technology, you want to build something that is hidden, get rid of the 90-degree angles, and then any sensor will, including optical sensors, will not have the reflection come right back to the source who's trying to detect. All right, corner reflectors, interesting technology. By the way, it works for any angle. I'll just give you some others. All right, so we're done talking about reflection. Pretty straightforward, how it forms images, how things reflect off 90-degree angle mirrors, surfaces, and now I want to talk about that other aspect of light coming into the interface between two surfaces, the refracted ray. And I have changed my notation, as I promised, to be consistent with our book. We'll talk about one here where the ray comes in, okay, and it is still the angle with respect to the normal, and two is the angle that comes out. Index of refraction where it comes in is 1, index of refraction where it comes out is 2, and Snell's law still applies. And I've shown two cases here. Okay, this is what I think I called as an external reflection, right? The source of the light is in the air or the lower index of refraction medium, the place where the sound speed or the light speed, I guess, in optics is greater. Okay, so this is the bigger end's big here. I'm sorry, I got that backwards. And small here, I said that exactly backwards. Okay, this is like index of refraction equal to 1, or maybe 1 point something that's fairly low. And we're going into a higher index of refraction medium where the light moves slower. Okay, so this is N big, which means velocity is less. Okay, so so this is velocity is bigger, and this is velocity is slower. And you notice what we said happens. The light gets bent. This is the animation I showed you. The light gets bent towards the normal. Theta 2 is less than theta 1. Okay. And this ray is called an externally reflected ray. This is just a transmitted ray bent towards the normal. All right. N2 greater than N1. Big N2, little N1. On the other hand, I could have what I called an internal reflection, where the light source starts, say, in the water or in the glass. And I get theta 1 and theta 2 here. Notice where it starts is 1. The angle where it goes to is 2. Where it starts, the index of refraction is 1. Where it goes to, the index of refraction is 2. And Snell's law applies. And something kind of interesting here. Now the light bends when I go from, let's see, this is fast speed of light to slow speed of light. Okay, because the index of refraction here is, say, 1 or some smaller number. The index of refraction here is some greater number, indicating a slower speed of light. Remember, we defined the index of refraction to be the speed of light in a vacuum divided by the speed of light in the material. Okay, and I don't know why I'm subscribing that with a 1. That could be 1 or it could be 2, depending on which material I'm talking about. All right, and so that's how we defined it. We defined index of refraction. A little bit on the basics of refraction. Okay, the incident, reflected, and refracted rays all in the same plane. Okay, I didn't have a third dimension where these things were coming out of, so that makes life a little bit easier for us. Everything happens in a plane that we can draw on a piece of paper. A ray entering a higher index of refraction medium bends toward the normal, and that's the case that I'm showing here on the left. A ray entering a lower index of refraction medium bends away from the normal. And then what we showed in the simulation, the wavelength must change. Okay, if the wavelength is the speed over the frequency, which it is, okay, then I can look at the speed as being the speed of light in a vacuum, c, divided by the index of refraction. Okay, and I guess then we take the speed of light divided by the frequency, and we call that thing right there, we call that the vacuum wavelength. the wavelength that it would be out in air or in a vacuum, and we divide that by the index of refraction as well. And so you can see the wavelength in the material will be shorter than it was in air or in a vacuum, because n is always a number greater than 1. Okay, the fact that n is a number greater than 1 puts some real constraints on the problem, and that's what I showed you in the simulation earlier. Now, image formation by this. Okay, so let's take a look, and if you've ever looked at a pond or in a pool, okay, the bottom always appears to be shallower than it actually is. An object floating around like a fish seems to be shallower than it actually is, and here's the reason why. If I have a real object, either the bottom or say a fish or something moving around in the water, if you look, I've got the incident angle right here, and this is an internal reflection if it was to reflect off, and some light would, okay? But in this case, we said the light bends away from the normal, so theta 2 here is greater than theta 1. I could do exactly the same thing on the other side. The light bends away from the normal, not drawn here, but there's my angle 2, and it's bigger than angle 1 over here. And so if you look where these two rays appear to be coming from, they trace back to this point right here, okay? There appears to be an image formed back here. Now, we'll call that virtual. Yeah, I guess I do have to agree. It is a virtual image because the light is actually coming right from here, okay? And if I put a screen there, there would be no light. So the object appears to be closer to this surface right here than it actually is. A little bit on the math of this, a little bit of trigonometry. If I'm looking to find theta 1 here, that angle right there, it would be the distance L right here, which is arbitrary, but divided by where the object is. Remember, we said S would be the symbol we're using for where the object is. And then theta 2 here, this angle right here, it would be the same L divided by this image. And it is conventional for virtual images to call it negative. Okay, so it looks like L, I said, was arbitrary. If I set the two L's equal to each other, so it's S times tangent of theta 1 and minus the image distance times tangent of theta 2, I got one equation right here. On the other hand, Snell's law still applies. So I have another equation with the relationship between N1, N2, and these two angles. Okay, and so if I put this all together, I can work out a relationship in the approximation, I guess, where these two are about equal. Then S is to N1 as the image distance, S prime is to N2. And the only thing I have to assume is that my angles are fairly small when I'm doing this. So if I want to find where the image is, I just solve for it. It's the ratio of the index of refractions to where the object actually was. And you can see since N2 here, I guess, is a number smaller than N1, since we're doing an internal case here where we're starting in this material, S image will be less than S object. Okay, forming a virtual image, things in the water or in the glass appear to be closer to the surface than they actually are. You'll see a problem on the worksheet that makes you draw these rays. And I don't think I make you actually calculate the distances, but there's a homework problem where you have to calculate those distances. Here's the equation. But like a lot of these equations, you have to couple it with a picture. And so this diagram I took right out of your textbook, as are these equations. But if you have any issues, go right to this equation and this picture and just fill in the appropriate places where the appropriate numbers where they belong. All right, image formation at a plane surface. It is a virtual image. I think that's all I want to say. There is a possibility, and some of you saw it when you were calculating what's the biggest order in interference or diffraction that you might have. There was a physical constraint that, can you have an angle right here, theta 2, bigger than 90 degrees? And the answer is no, you can't. Okay, the biggest that theta 2 can ever be is 90 degrees, and that gives us a phenomena called total internal reflection. Theta 2 can never be bigger than 90 degrees. And so the sine of 90 degrees, that's just 1. It appears then that the incident angle is limited in those cases when we're having an internal reflection here, right? We're going from, I guess, a slower medium to a faster medium. So we're going from like glass to air or water to air. The biggest we can have here is 90 degrees in this case. And so the biggest incident angle you can have and still be less than 90 degrees would be the ratio of N2 to N1. We call that incident angle, where the transmitted angle goes to 90 degrees and that goes to 1, we call that a critical angle. It's the critical incident angle beyond which you don't get any transmitted angle because you've already hit 90 degrees. And then what must be left is that everything must be reflected. It's then called total internal reflection, 100% reflection. I got a couple pictures of that. Okay, and so here's sort of the idea, and I've shown this. That's the incident angle right here. There's the incident angle right there. There's the incident angle right there. There's the incident angle. For these guys, you're way less than this critical angle, and so you're going, it's an internal reflection, okay, glass to air, for example, or water to air. And for these cases right here, where the incident angle, the theta 1, is less than the critical angle, light transmits through just fine. Some of it's also reflected, but you get a mix. As soon as you hit this critical angle, this thing has reached the 90-degree limit. It can't be any greater than that. And so the light is completely reflected inside, in this case, the glass. Over here, you can see I've got another image of a fish tank with half the fish tank filled with water, the top half filled with air. And you can see in this case, you're less than the critical angle. There is some light reflected, hard to see, but there's a significant amount of light transmitted through into the air. And then over here, the angle gets a little bigger, right? But still less than 90 degrees. You'd probably still have some light reflected back in, just very dimly visible. But right here, you exceed that critical angle, the light might try to run right to 90 degrees. That's as big as it can be on this transmitted, okay? But once it tries to go beyond that, everything has to be reflected back. You know, the back of a fish tank often looks like a mirrored piece of glass if you look at it from an oblique angle. If you look at it normally, you can see through it, but you look at it from the side and you can't see through it. It looks like a very shiny piece of glass, and that is evidence of total internal reflection, because the incident angle you've got is greater than this critical angle. Right? It's an interesting mathematical kind of physical phenomena, but it has tremendous practical applications. Where'd I go? There it is. My image of this guy right here. This is meant to be a light fiber, okay, just greatly exaggerated. And you can see for very high angles, okay, which you kind of restrict this bend here so that you can have a big angle right here, everything gets reflected inside the fiber. And then if it hits again, hopefully everything gets reflected. Any ray coming in, you're hoping is trapped inside the fiber for by means of total internal reflection. Okay, and so that is the point here, I guess. Fiber optic technology exists. You start with a laser beam sending light in with some signal that you want to transmit down this long fiber in it, and it's stuck. The light is stuck inside the fiber. As long as you don't make this kink right here so big that you're less than the critical angle, as long as all the rays kind of glance off at greater than the critical angle, you'll always get total internal reflection. It's impossible to get a refracted ray because you're greater than the critical angle. Okay, and so it's an effective technique. Now you still have losses on fiber, but all the losses are due to absorption of the glass taking energy away from the light. And so in any fiber optic system, every couple of miles, you have to have some sort of system that boosts up the energy again, but it's not due to any loss through the edge of the fiber. No light comes out that way. It's only because the light gets absorbed by the glass, which is the fiber. And so this is an amazing technology Verizon and some of the others have exploited. Instead of putting copper wires in to bring the cable into your house, they're using fiber and putting the signal on an optical laser beam that they inject at their transmitting site. All right, last thing I want to talk about, and then we are done, is what I said before. In this index of refraction, it does indeed vary with the frequency. And remember, frequency of light corresponds to color. And so if within the visible spectrum even, you have differences in color that are slight, but you can see for wavelength, visible light varies from somewhere around 400 to 700 nanometers, with yellow being near the middle here, okay, around 490, 500. Red is over here. Where are we? Yeah, where do I have yellow? I thought yellow was a little lower than that, but they're saying yellow is right in here in the 500 region, 550 to 570. I'll go with it because I'm not an optics person. So there's yellow, there's red right there in that range. You can see that although not significantly different, red light in a piece of glass might have an index of refraction of about, 1.64, whereas, blue light over here has an index of refraction maybe 1.62 to maybe 1.64, just two slightly different values for the index of refraction right here. Okay, and so what does that mean? I guess the red or red light over here will have one angle of refraction, and it occurs at two places in a prism, right there and then right here again. Okay, whereas the blue light has a slightly different value of index of refraction, and with two surfaces of refraction like in a prism gives you a significantly different angle. Okay, and so I guess this is the proof that index of refraction absolutely does vary slightly with the color, the frequency, and it's observable, and you have to pay attention when you quote an index of refraction. Well, what color light am I talking about, or what frequency of electromagnetic radiation am I talking about? I think that's the last topic I want to talk about here, and we'll call it a day. I don't know if I'll see everybody again as a group. I do want to tell you it's been a pleasure working with you all this semester, and I wish you the best for you seniors that are about to graduate. I'm sorry that your graduation just isn't going to happen in person, but that in no way diminishes the achievements that you've had over the 4 years you've been here. For those of you at the other end, the freshmen, I hope your studies at Washington College are successful the rest of your time here. And a couple of you who are thinking about physics as a major, I highly recommend it. Some of you have real aptitude for the subject, and it would be, I think, an exciting thing for you to go on to do. Those of you in other science areas, keep on chugging, and best of luck to you here at Washington College. I think that's about it. I'll stop sharing. Any questions on anything I've said today about the exam, about the material? All right. Yep, go ahead.
Do you have time to go over worksheet 36? Because I can't come to office hours
today.
Sure,
I can hang around for a little bit afterwards. All right, let me stop.